Uh-oh, it broke out the wrong way. Go the other way. There we go. Do you have the right angle again?
Well, let's see if it finds it.
Oh, it's on the one side.
No. Hey. Oh, very cool. Hey everyone, welcome to experiment number 3, and in this one we're going to be navigating again, so autonomous navigation, but using a sonar sensor. I'm also introducing a little bit of 3D printing. I believe 3D printing is an important topic to learn about, and if you get a chance you should get a printer and start printing your own parts and also designing your own parts using some kind of a computer-aided drafting program. So in this experiment we're going to have a sonar sensor, and sonar is it's a sensor that you can see right here. We have a little sonar sensor. It's a sensor that looks like this. And so sound gets emitted out of these little guys, and then when it touches something in front of it, it bounces back to the sensor. And so the sensor has a little chip on the back that can do some little bit of a conversion for you of that signal into a meaningful value that comes out of these wires. The sensor itself is fairly simple. Let me see if we can have here. It has a ground, it has a voltage of 5 volts, it's got a trigger and an echo. So you have to trigger the circuit on this guy to start putting out the little sound waves. And the human ear can't really hear it, although some people can hear it a little bit. You can hear the little ticking sound coming out of these guys. And so there's a trigger to tell it that to send a signal at a particular level, and then there's an echo that receives this guy. So we'll go into detail a little bit more, but let me show you a quick video of what that looks like. So you have the little robot here with a little bracket that was 3D printed, and you have your sonar sensor, and the robot is rotating. The sensor is rotating. Okay, so it rotates 180 degrees. It's looking for an opening, and when it finds an opening, it'll get out of there. So I'll show you real quick part 2 of that video. So it continues to search for an opening using basically like radar technology. So it sees that there's an opening there, and it's gonna try to get out of there. So okay, so we are not going to be using the front of the sensors. So basically the little switches, we're going to remove them so that they're not in the way. So these guys, we're not going to be using them anymore for this experiment. So why don't we remove them? You have your screwdriver. And that way you only have this, and you have the front, and you'll have your sensor bracket. If you don't have a 3D printer, the robot comes with a sensor bracket that you can use. Right, so you have this plastic bracket. But if you want to, you can design your custom sensor bracket. So let's talk a little bit about that. This is the robot with the bracket that's included. Sometimes you'll have different color brackets in there as well. But you can 3D print this. You can download a program called OpenSCAD if you want to draw your own bracket. Some people have given it different shapes, like Mickey Mouse ears and different things, like a Batman bracket also. But OpenSCAD is a computer-aided design software that is programmatic, and I like it because you can do line-by-line programming to create a bracket. So for example here, this is like C code a little bit. You can define the holes, you can define cylinders, and then you can cut holes in the different rectangles and things like that. So I designed this particular bracket using OpenSCAD, the free software that you can download. But you can use anything else. You can use Fusion 360, you can use SketchUp. There's a whole bunch of programs out there that you can use. Okay, and then you can save what's called an STL, and this is the file that 3D printers can process. Okay, so then you grab the STL file, you load it into your printer via whatever software your printer uses. Here's other designs that I created on using OpenSCAD. Okay, so this is the bracket, and like I said, it's not too difficult, right? You can kind of figure out some of the lengths and all those things that you need. But again, you're welcome to use other ones. Here's what the finished product looks like. You have your bracket. In your bag or box of the robot, you have extra horns that you can put in and glue to it, and so you can put the sensor to the bracket in there, and then you mount it to the motor, to the little blue motor or black motor that's in front of your robot. In this case, this one was like a little black color motor. It's in servo motor that's in here. It's a mini or micro motor. A mini motor, basically, mini servo motor. Okay, and so once it's in there, put the little screw in there to secure it. Here's what the sensor looks like again. Okay, here's what the sensor looks like mounted already. Ignore all of these other things here. That's for other projects. Okay, so the sonar sensor emits an ultrasound at 40 kilohertz. It travels through the air, and when it hits something, it bounces back to the receiving signal. Okay, so this guy can go anywhere from 1 inch to 13 feet to detect something in front of it. It uses a 5-volt power supply. It's the effectual angle is about 15 degrees. So on the front of it, you're looking at about a 15-degree, pretty narrow beam as far as the how much it can actually detect. But again, it does go from 1 inch to 13 feet. So this is how we connect it. It's very simple to connect. Again, just connect it to our middle row here. Put in the power for 5 volts, the ground, and then 2 pins are going to be used to do a trigger and an echo. So you got pin number 6 and you got pin number 12 here. Okay, so in the code, those are the pins that are going to be defined. So make sure that you connect that correctly. Now there's a lot of libraries out there that you can download for this thing, and they're all included in your folder. There's a lot of samples, and there's a lot of libraries in there that are included. But in this case, we're going to show you how to do it manually with no library. Okay, so this program does not use a library. Okay, so I'll type it in here. This program does not use a library. So this is how you would trigger everything manually, basically. Okay, so you're going to, here's how you trigger. You can write a digital signal between 0 and 5 microseconds. Okay, and then give it a short pulse beforehand, and to ensure that it's going to be a clean high. And so then you can do a high signal for 10 or more microseconds, and so that starts the whole sensor to start sensing, basically, and start sending and receiving. Okay, and then you're going to detect the signal. Okay, it's a pulse in function. This is a brand new function that you haven't seen, and it's going to detect it. And then we're going to do a little conversion. This is thanks to the formula for the speed of sound. We'll be able to do some conversions of distance and duration. And then we're going to print it on the screen in inches or in centimeters. That way we can tell what the distance is. Okay. So once you run it, you can open the serial monitor to see what the output is, and that should be good for you to test. Okay. And okay, so no library. Now there are some libraries, and you can download them and install them on your Arduino board, or your Arduino software. Put the libraries in the software in the Arduino folder, library folder. There's this one called New Ping, and it significantly reduces the amount of lines of code. So we're using the New Ping, and we're gonna see here that you only need basically these lines of code to make the same program that you did up here, where it's all manually done, triggering manually. The New Ping library automatically does all those things for you very simply. So it's pretty interesting how that works. Alright, so I'm going to go ahead and remove the switches from the front and connect the sensor, and then we'll get to try some of this code right now. Okay, so I'm removing this guy, being very careful to pull this out right from here. So now I got that out of the way. I can refer back to my manual, and I can see that trigger is pin number 6 and echo pin 12. So trigger 6. Trigger is, in my case, it's brown, so it goes to pin number 6 on the output of it. So the signal wire. So it goes into the signal row, which is right on the outside. Okay, and my other one goes to 12, which is echo, which is red, and red goes to 12. Again, they go onto the signal. See if you can see it. Okay, and then we have 5 volts. So that you can plug into any 5-volt source that you like. So in this case, I'll just pick the middle one here in the first one, and then the last one is ground, so just pick any ground signal that you like. I'm just going to pick any ground signal that I like under the middle row here. Okay, so they're all connected now. Okay, so now I am ready to start testing my code, and we can start with the first one here. So let's quickly make a copy of this one. I'll grab it from here. And let's see what this guy does. I'll go ahead and open Arduino. I'm going to delete what's in there. I'm going to run it, but don't save it. If you do save it, you want to save it with a different name. Okay, so this one right here, oh yes, of course. I'm showing you all these different errors that I forget to do here. So the first thing is, of course, we got to plug in the robot. Plug it into your laptop, or you forget. And also, I like to put something underneath it so that it doesn't try to run away. Let's put a little box or something. And then last but not least, I'm going to turn it on here with the power switch. And that's the last program that we were doing. So let me run it again. And it's uploading, done uploading. So again, this guy is going to display on the screen something. So I'm going to use my serial monitor to see what that is. Okay. And so right now it tells you that it does see something around 60 inches from its location. It's about 100 and whatever 100 centimeters is. Let me show you right here real quick. Put it side to side. So if I put my hand on it, that distance is going to start decreasing. And that is true. That is about 3 inches between me and the sonar sensor, right? You can see the little sonar sensor there. Right, so if I go further out, you see that it starts to increase. Got to be right in front of it. Remember, it's only a 15-degree width here that it can handle. Okay, but ideally you want to see things within this distance, right? So that it avoids hitting things. Okay, so our sensor works. We can go ahead and try a couple more programs and see how that works. So let's see what our manual says. Let's try one with the new ping library. Now, do I have the ping library? So the way to check that is you can go over here to your C drive, go to Program Files, and if you don't see it in there, it'll be on the Program Files x86. Go to Arduino, go to Libraries, and see, I don't have the new ping library, so I'm just going to copy it from my lab. It should be on Beachboard. There should be a new ping library in there. Alright, so if I don't see the library here, then I'm going to have to grab it from, let's see, yeah, it's right here. So I do have it in here. Let me extract it. Okay, a new ping basically consists of examples and a whole bunch of other things. But all you have to do is copy that into your Program Files x86 under the Libraries folder of the Arduino folder. So if I say paste, continue. Okay, so now that I have the library in there, usually it's right away. If you go to examples, you can actually, let's see, should be right away. If not, you'll have to get out of Arduino, go back into Arduino. So I don't see it. So what I'm going to do is I'm going to copy this so I don't lose it. I'm going to close Arduino, open Arduino, so that it reads the library. It looks like, let's see, looks like it kept that that old program in there. So let's see. Let me load it up and see what it does. Okay, so actually this is the old program. Let me delete that. Go back over here and grab the new ping sample. And copy that. Look how short it is. Paste it into this one. Run it. If it runs okay, that means it found the library okay. And again, libraries can be found under examples. Every time you put a library in there, it'll put it in there. You can see that the new ping examples are there now. So this is pretty neat. It's got examples if you had like 15 of those sensors, for example. It's got examples of how to use timers because the robot cannot do two things at once. You can trick it into thinking that it's doing two things at once, but it's really splitting the time between tasks. So this is a really good example. We're going to look at this later on, but for now, let's run this guy. It's done uploading, so I should be able to open this up. And this one, just like the other one, right? If I'm putting my hand here, okay, I don't have the inches conversion in my code here, right? So, but I do have the centimeters. I can look at the previous example and see how I converted it to inches and do it that way. But you can work in centimeters too. It's pretty neat. Okay. 2.54 centimeters is equal to 1 inch, so you can do conversions like that. All right, so we'll continue with some other examples. So here's the information about the pinging and the echo. So on the sensor, one of the little eyes does the pinging. When it hits the object, it produces an echo, and then the echo is heard basically by the other little sensor speaker here. It's a little piezo material that can do these things. So you need to basically send a pulse, right? The start pulse. You need the start pulse first, and then you can send the echo time pulse that reflects back. Okay. There's also an LED that tells you when it's active. Okay. And again, you just need the 5 volts ground, the trigger sends the start pulse, and then the return pulse is the echo. Okay. And then it's divided by 2 when you do the conversion. It's divided by 2 because it does a round trip, right? So it goes in and out. So the little sound thing has to be divided by 2. All right, so here's another example. Look at this one. This one, you can actually connect the trigger and the echo together to the signal pin 6 of the Arduino. So in other words, this could save you an extra pin on the Arduino board. Okay, so sometimes you're running out of pins. Well, this library does a little bit of a little timing tricks in the back end of the library that allows you to put them in the same pin, and it divides the time between the sending and receiving in the same pin, which is pretty amazing. So you can use that one as well. It does provide you like a round trip function in centimeters, for example. So this one will show you, and it's actually not a function, but it is part of the library where it does the conversion for you automatically, 2 centimeters. All right, and then you get the information on the 0 monitor. All right, so let me see. So then there's other things that we can do. A little bit about timers and interrupts.
Let's say you're building a project using Arduino. and you have an event that you want to have happen every so often. Maybe every 3 minutes you want a servo motor to move, or maybe every 20 seconds you want to update a web server with the most current sensor reading. How do you create these timed events in Arduino? That's the objective of this series of lessons, that by the end you'll be able to program repetitive timed events using your Arduino. Now, if you've watched the previous lessons, we've talked about the millis function kind of in general, we've talked about tight loops and blocking code, and some issues that arise when using the delay function. Now, I want to talk about how we can use the millis function to create simple timed events. Specifically, we'll cover a quick review of the millis function. We'll think about the millis timeline. We'll use millis to create once-off timed events. We'll use millis to create repetitive timed events. And finally, we'll talk about how black holes can alter space-time. Let's start with a quick review of the millis function. I think the easiest way to review this function is just to take a look at it in a simple sketch. So what I'm going to do is write a sketch that prints the value of millis to the serial monitor window. So here we are in the Arduino IDE, and I'm going to begin in the setup and use the serial begin function to enable serial communication. Then in the loop, I'm going to use the serial print line function, and I want to print the value of millis. So every time through the loop, this program will print the current value of the millis function. So if we load this sketch onto our Arduino and open up the serial monitor window, you'll see the value of millis is increasing rapidly. So what is this value that the millis function returns? Well, the millis function returns the number of milliseconds that your Arduino board has been powered up. So as soon as your Arduino board is powered up, the millis function begins tracking the number of milliseconds that have passed. It starts at 0 and it counts up and up until it gets to 4 billion and some change. And then it overflows, which is just a fancy way of saying that it starts counting back at 0. And it would take 49 days for the millis function to overflow. So the number of millis gets real big, and it gets big pretty quickly. Now, the way millis is able to track the number of milliseconds that have passed is by using the timer counter module built into the integrated circuit that the Arduino uses. In our Arduino code, we don't have to start the clock or start millis. It starts all by itself in the background. Now, if you want to learn more about how the millis function works, definitely check out the first lesson in the series. So how can we conceptualize millis so that we can use it to create timed, repetitive events? Well, let's start by thinking of millis as moving along a timeline. So the timeline starts at 0 and it goes all the way up to 4 billion and some change. And again, these numbers represent milliseconds. So at any point during our program, we can call the millis function and find out exactly where we are on the timeline. So let's go ahead and zoom in and take a look at the first 5 seconds of a program. So this little dot represents where millis is on the timeline. And for the sake of explanation, let's slow down that dot because I really can't talk that fast. So as soon as we power up Arduino, the millis function starts counting. So you can see the value is increasing, moving to the right along the time axis. Now, if we want to create timed repetitive events, how could we use this timeline to our advantage? What if I reached out ahead in time and I made a little hatch line and I said, when the value of millis gets here, do this thing. In code, it might look something like this. So let's talk through this sketch from the point when power is first applied. So power is applied, we get into the loop, and the first thing we do is check millis. Since we just began, the value of millis is low. It's less than the value of event 1, which was 1,000. So this if statement condition is false, and the code in the curly brackets doesn't run. So this loop continues to execute over and over, and the if statement keeps getting passed over because the condition is false. But that really doesn't last long, because before we know it, the value of millis has exceeded the value of the event 1 variable. So now the if statement condition is true, and the code within the if statement begins to execute. So now we've created a timed event using millis. But this really isn't exactly what we're after. It might work for some applications, like let's say you're building a radiation warning exposure timer. And say when you flip on a switch, it turns on the Arduino, and when so much time has passed, an indicator light is turned on. So after a defined interval, an LED turns on, and then it just stays on. Now, we could have used the delay function to achieve the same thing. But what's nice with using Millis is that since we didn't use the delay function, we can do other stuff in the loop. Maybe we can read a sensor or update a display or whatever. The Millis function won't block other code from running like the delay function would. Furthermore, if we wanted to, we could add more events that trigger at later times. So this is one way to use Millis. But it's really not what we're after. We want to create repetitive timed events. For example, every 30 seconds, maybe we want to read the water temperature. Or every minute, we want a servo motor to move left and then right again. For these types of programs, this simple use of Millis won't do it. So let's go back to our timeline. So here we are at the timeline again. And I'm thinking, what if we do this? What if we still have our hash mark, right? We say, when Millis gets to this value, then we want to execute our event. But now what we'll do is when the Millis value gets to this point and our event code runs, what we'll do in part of our code is update the event time. And so essentially what we're going to do is move that hash mark down the timeline to the next point. So every time we get to that hash mark, we also update the hash mark for the next time around. It's kind of like we're holding this carrot in front of the Millis function, like, here, come get it. And then when the Millis function finally gets there, we move it further down. That's just kind of mean. So let's try some code and see what this might look like. So here we are in the Arduino IDE, and the first thing I'm going to do is set the interval of the event. So I've created a constant and I've named it event interval. And the reason I have it as a constant is because the interval isn't going to change. I want my event to happen every 1,000 milliseconds. So now what I'm going to do is I'm going to create a variable that I'm going to use to update the time. I'm going to call it previous time. So let's do that. So I've created previous time and it is an unsigned long. And the reason these are unsigned longs is because the value of Millis gets extremely large, and we want to be able to hold that value in our variable. I talk about this in one of the previous lessons, so make sure to check out one of the earlier videos in the series to learn more about that. Now in the setup, I'm going to go ahead and start serial communication using the serial begin function, because in the loop, I'll be sending some stuff to the serial monitor. So I'll do that now. Now down in the loop, what I'm going to do is create a variable, and it's going to get updated every time through the loop with the current time. And how do I get the current time? Well, I just call the Millis function. Remember, the Millis function is going to report back to me where we are on that Millis timeline. So I'll do that now. So I've created a variable called current time, and I set it equal to the output of the Millis function. So every time through the loop, current time is going to be holding the current value of the Millis function. So now comes the key step. I want to create some type of function that is only going to happen when I'm at my event interval. So every 1,000 seconds, I want something to happen. So the code I'm going to use is going to be an if statement. And the condition here is what is key. So what I'm going to do is go ahead and write this if statement, and then we'll talk about it. Okay, so this kind of looks like a doozy, but let's just talk through this. So what does this if statement do? Well, it takes the current time, and remember, the current time is constantly being updated through the loop with the Millis function. So it takes the current time, it subtracts it from the previous time, and then it checks to see if the value here is greater than or equal to the event interval. Okay, so let's just really nail down these events right down. Let's put some numbers to them. So we know event interval is never going to change, right? It's a constant, and we set it to 1,000. So you can just think of this as 1,000. And now we've got two other numbers here. We've got current time, and we know this value is always going up, right? Because this is the value that we're getting from Millis. So think of current time as just, it's almost like a big arrow up. It's always getting bigger and bigger and bigger. So we've got something that's getting really big, and now we've got to ask, what is previous time? Well, previous time starts at 0. So we've got a number that's 0 here, and then we've got a value here that's current time. So the first time through the loop, the difference between current time and previous time is going to be small. And that's because we just started the program, right? So millis, it starts at 0. Maybe millis is at like 100. So we'd say, well, 100 minus 0, that's 100. And we'd ask, is 100 greater than or equal to 1,000? No, it's not. So this if statement, all the code inside here wouldn't run. And so we'd get to the end of the loop and we'd start right back at the top. We'd assign millis, the value of millis, to the current time. So let's say now it's 200 milliseconds. All right, so now current time is 200. We get back to this if statement, and now we ask, all right, is 200 minus 0, is that greater than or equal to 1,000? It still isn't, so we skip this if statement. We would keep doing that over and over until a second has passed. When a second has passed, then the millis function is going to return 1,000. So now we'd say, is 1,000 minus 0, is that greater than or equal to 1,000? We'd say, hey, yes it is. Sweet. So we can jump into our code. So the event code that I've got here is just printing something to the serial monitor. And then what we do, and this is kind of the trick, this is how we scooch down that hash mark so that the next time around we can have this event happen again in another 1,000 seconds. So what we do is we take the previous time, which was 0, and we update it with the current time. And we had said that the current time was 1,000. So now previous time is now equal to 1,000. Okay, so we've updated that time. We exit the if statement, and then we come right back into the loop. Now current time is going to get updated again, right? So maybe it's like, I don't know, 1,000, let's just say 1,010 milliseconds. So now we've got 1,010 here, and we've got to subtract 1,010 from previous time. Well, what was previous time? Well, we had just updated it to 1,000. So what's 1,010 minus 1,000? Well, that's 10. Is 10 greater than or equal to 1,000? Nope, it's not. So we skip over this code. And you can kind of see what's going on here. We're going to keep skipping over this code until another second has passed. Because when another second has passed, then millis is going to be 2,000. And we'll ask ourselves in this if statement, is 2,000 minus 1,000, is that greater than or equal to 1,000? We say, yeah, it's equal to that. So then we can run this code again. And you can see we'll print out to the serial monitor our event code or whatever code it is that you want to have happen at that specified time. And then we update the previous time again. And this right here is the coding paradigm that is going to allow you to create repetitive timed events using your Arduino. So I know it can look a little tricky. Seems like there's a lot of variables. The best way to really get a handle on this is just to write the program yourself and mess around with it. All right, well, let's just do a quick review of what we talked about. First, we did a quick review of the millis function. We said, hey, you don't have to start the millis function. It's just always counting. It starts at 0 from when the time the Arduino is powered up, and it counts up to 4 billion and some change, and then it starts over again once it gets to the top. Then we talked about kind of thinking about millis moving down a timeline in our program. This is kind of a way to help us conceptualize how we can use millis to create timed events. Then we talked about creating once-off timed events using the millis function. And finally, we talked about creating repetitive timed events using the millis function. Well, hey, I hope you found this lesson helpful.
All right, so hope you enjoyed that video on using the millis function in Arduino. And so here's an example of timers and interrupts. So the thing about it is Arduino cannot run two things at the exact same time, but we can pretend it by splitting the time between a couple of things and kind of pretend like they're running at the same time, but they're actually splitting the time in between them. So I'll show you real quick here. So in this example right here, we are using the millis, right? So we're going to say ping timer equals millis. So we're starting the system time. Okay. And what we're going to do is we're going to do certain things in the program, and we'll be able to do other things that it looks like we're doing it at the same time. So I copied this into my Arduino environment, which is a lot easier to read. So I'm using the new ping library, and I have my sensor connected to the same setup here. I'm using the ping timer equals millis, and so that way I don't need to use the delay function, right? So if millis is greater than or equal to the ping timer, right? So we have let's see, where is the ping timer, unsigned long ping timer, right? So if millis is greater than the ping timer, then it's ping timer plus equals it adds 1 to the ping timer plus the ping speed. So, and then it puts out the it calls the echo check function every 24 milliseconds, so you can check that ping status. Okay, that ping status. All right, so this does the checking. Okay, and what we can do is we can actually put in a few more things to do over here besides checking for the ping results. So why don't we make it do a couple more things, or one more thing. Let's see, why don't we have it say something like okay, squeeze another line here. Okay, so I'm going to show the results, and I'm also going to show a brand new line, and I'm going to make it pretend like it's doing it at the same time. Okay, so unfortunately, because of the timer 2 uses the it basically it uses up the sound function, and it also uses up the servo function, I believe. If you remember on the video, I told you what it's eating up. So the timer 2, we cannot really do some of those neat things, but we can do other things. So let's run this guy. I want to show you real quick what that would look like. So let's make sure the robot is turned on. All right. So you see how it splits the time, but see how smooth it can actually read the distance, right? And this is, I wanted to show you both at the same time actually. All right, so you can kind of see how smooth it reads it, but it also adds in between that other line that I'm printing, okay? To show this a little better, let me show you another way that we can do this, and that is I can say, instead of saying print a new line, I'm going to print it on the same line. Okay, so I'll just do a print. And over here, you can see that it's printing the line, but at the same time, it's also printing the distance, right? So it's pretending like it's doing the two things at the same time, but it's really splitting it into two different jobs here. All right. So the next thing is we can look at some other examples. There's a lot of examples here. There's another one called Ultrasonic Library. And this is a little better one because it simplifies things even more. You just have to write a couple of things like the pin number that you're using for the trig and echo. And that's it. You can output the, the data right away. So it's amazing. Here's another example using the ultrasonic one and a timer. Right, so we're using the millis also, but it's using the library part of it. So you can try all of those. You can download those the library, like the ultrasonic library also. This one is going to be scanning the area and reporting back the output in an angle. Okay, so this one right here, we're going to have to connect our little servo motor. Okay, so our servo motor goes to pin number 9, and you can see that our little servo motor is attached down here, this guy, right? And it has its own little cable. Okay, so the yellow one would be the data, then brown is ground, and red is the power. Okay, so I'm gonna try to see if I can squeeze it in here through. Actually, it doesn't matter. It can go through anywhere. Just here is fine. It's got to be able to reach all the way to pin number 9 on the sensor shield. Okay, it's plenty here. So pin number 9 is actually right here, empty, which is good. So I got it connected to pin number 9, right there. Okay. So this one right here, let me see if I actually have the ultrasonic library installed, but if not, I can always look here for the library. Ultrasonic, I'm going to extract. Okay, so it looks like that would be it. So I'm gonna grab that, copy it, and I'm gonna, in case I don't have it yet, which I think I don't have it, put it under program files x86, Arduino, one, Arduino, libraries, and pretty much did not have it. So I'm just gonna put it in there. You need permissions, yes. So now I'm going to close it. Okay, so let's open up Arduino and we got our new program. Let's see, let's make sure we increase the font size. Let's look at our example here. So ultrasonic servo rotate, we have our servo, we have our sensor, and let's see, in this case we have, okay, make sure that that's 12 and 6. I believe that's what we have for the echo and the trigger. Okay, so let's copy and paste this example. Go. Okay, so it's uploaded. Yeah, so it looks like it's working. And here we go. We have a couple of let's look at what the robot is actually doing. So what this is doing here is it's actually giving you the angle, and then it gives you the distance that it measures at that particular angle. Right, so if I put my hand closer on this side, which is about the 180 degree mark, see how low the number is, right? Compared to getting closer to the upper level. Right, if I take my hand off, these numbers are going to be increasing in size because of the distance that it sees something at. So the closer that you have an object, the smaller the numbers will start to appear here. See how small the numbers are? So that means that the bigger the number, that means there's nothing in front of the sensor. So if you're going to make this robot go through a door, you want to go through where that biggest number is, because that means there's nothing in there in the way. Okay, so the angle, it goes from 0 to 180 degrees, right? From the right to the left. And then it gives you an estimated distance in centimeters, how far something is from it. Okay, so pretty neat. So we can use this data to start some navigation. Okay. I'm going to turn it off here. And this gives you a little bit of an explanation of what it is. Right, so the servo is rotated 180 degrees, so the sensor rotates with it twice in each direction, and the readings from each direction are averaged to get a better estimate of the distance. The two important things to mention here: some time must be allowed after the write command before reading the sensor to ensure the motor reached the position. Right, so there's a few little things that are happening, and so you got to give it time in order to see it. If there's nothing in front of it, sometimes it takes even a little bit longer. Right, where there's empty spaces, it takes a little bit longer to update that number because it's a big number. All right, this one is just a little sample with a ping sensor, not rotating, just a ping sensor right in front, just like you see it here. Just like that, but it can navigate. You can point it in the mirror, you can navigate with it. If you see something, it backs away, but it's not rotating. The final lab, you must have it rotating and escape. Okay, just like I showed you in the video earlier. Okay, let's see what else we got here. Okay, so we're connecting the servo motors. So it's a good starting program to get going here. Okay, just the sensor looking straight ahead. And this one is pretty neat, just a little extra credit, right? Just extra sample. So this one is going to be not required, so not required to do this one. It's optional. Okay, so let's do this. But this one will follow you if you put your hand in front of it. And so this is going to start helping you to create the Sumo robot lab. Okay, so I'm trying to get you started thinking about the rest of the labs that are coming up. All right, so this one scans back and forth between 0 and 180 degrees smooth. So there's more turning turrets examples here that you can use. And this one, that's all it does. It just basically turns it, scans it. Here's another one. This one also does the same thing, but it outputs the sonar ranges at the same time using timers. All right, so maybe we want to try this one right here. Let's see. Oh, this one also has some motors in it. Well, let's see if it works and if it moves. But for now, we're interested in making sure that the turret moves and that we get some real time, as much as real time as we can. Let's see what this does. So it's uploading. Done uploading. So make sure I have my robot off the wheels off the ground so that if it starts to move, make sure we turn it on, and it looks like it's doing something. It's going really fast. Okay. This might be turning a little too fast, so even with timers, it's not capturing the object in front of it as well. Let's see what we're doing over here. Okay, so that's more like it. Let's see if this is, yeah, okay, so that's pretty good. And it's rotating. Oh, let me show you what it actually looks like here. Okay, so you can see it right now. Looks like it's doing some rotation. It's going forward right now. So if I put my hand in front of it, let's see if it sees it. Okay, so there's a little delay. You saw it in there. What about over here? Okay. So there's a slight delay, but it should be expected. So this one is running okay. You can probably slow down the rotation a little bit and get more accurate results over here. Alright, so this is a good program. It's almost solving for the solution, but it's going to be up to you to come up with this program. This is just an example I'm showing you. So these are just, they're not included. You're going to have to figure it out. But it's just an example. Here's another one. And there is a full-on solution here. Let's see, this one is also using timers. So I'm going to give you all the samples that where you can learn more about how to use the timers. Okay, and then it looks like we have a final code. Let's see how this one works. It might be very similar to that last one that I just showed you, but it might be a little more smooth. Okay, so I'm also using millis in here. And it looks like I'm checking at different degrees here. Alright, so it's done uploading. Let's open up our camera. And this one just gives you a little bit more information. So let's turn the motors on. Yeah, see how much smoother and slow this is turning. So this is the kind of motion that you want. Okay, so this one, let's see how well it detects something in front of it though. There you go, it's backing away now. Yeah. Alright, so this one has a little bit of an issue, and it's to be expected every time you build a robot. Depending on how I connected it and how the code looks, it might have some differences. So let's check out the code for a little bit here to give you an idea. So we have the trigger pin at 6, echo pin at 12. So that's correct. We got our little speed for the motor. And let's see, what am I outputting anyways? What's my... okay, looks like yeah, so like I wanted this actually. I wanted to test the sensor. And so let me see if I can do this. Let me uncomment it. And I want to see what the sensor is looking at. So I also need to uncomment the sonar.ping timer echo check so it can actually output the data. Okay, so I uncommented that, so now I can look it up on the screen and I can see what's going on. So let's upload that guy. So let's open up our screen here. And guess what? I gotta turn the robot on. And so now it reacts. It tells me what direction it's moving. Right? So it comes here. It tells me it's moving forward, but the moment that it sees me, it tries to go into another direction. Okay. So it's not perfect, but it's really good. It's at least reacting and it's at least moving out of the way. Okay, so it's gonna try to find an empty space and go in that direction. That's really all it's doing. All right, well, let me play for you again the video of what it's supposed to be doing, and we'll take it from there. All right, have fun with this one. Okay, so it's supposed to be looking around. So it's looking pretty far out to see if there's an opening somewhere. Still hasn't found it. So let's see what it does when it finds it.